Hello. In this video, I want to talk about some additional aspects of regression analysis. So let's start by going to our Moodle page, and you should be able to find a data file there near the top called multiple regression. So let's open that up. And we can see from our variables window here that we've got 3 variables. Always like to summarize the data quickly to see what I have. You can see that I've got 15 observations for each of these 3 variables. I label them y to indicate the dependent variable, but the x1 and x2 are both going to be independent variables. Well, let's start by looking at the relationship between y and x, and look at it graphically first. So I'm just going to issue a command here to make a scattergram. And you can see that there seems to be a positive relationship between x1 and y, that if at high values of x1 you're going to see higher values of y. Let's take a look at the actual regression analysis and see how good this fit actually is. There's our familiar box. Remember, we're looking first at these 2 values here. The probability is far less than 0.05. It's essentially 0 out to 4 decimal places. So that tells us the chance that that relationship arose just by random events is virtually nil. And we can see our r-square value. Remember, this r-square can be at most 1. So this is pretty close to 1. So what that means is that if we know what x is, we can predict what y is to a pretty good degree, that we can explain 91% of the variation in y knowing what x is. Let's take a look at the second independent variable. So I'm going to take advantage of my catalog here, and this time we're going to look at a scatter plot. And what we can see is, again, a positive relationship between our independent and dependent variable. Looks like it's a little messier, a little more variability there. Let's take a look at the regression analysis. Again, I'll just pull down my old command and alter that. So here's our familiar plot, our familiar box. The probability, again, is very low, so this tells us we have a statistically significant relationship between the 2 variables. You can see the r-square value isn't quite so high. Still pretty good, but not as high as the 0.9133 that we had here. Now, what I want to do now is to think a little bit about your high school algebra class. And you remember that when you were taking that class, that you developed an equation for a line. That line equation was y equals mx plus b. And m was the slope of the line, and b was the y-intercept of the line. You can get that information from the regression analysis here. And that, in fact, is what these 2 variables are here. x2, the coefficient for x2, represents the slope of the line. And this value here, this constant, represents the y-intercept. So for this equation here, if we wanted to write it out, we would say y equals 0.284, rounding, times x2 minus 0.098. So that would be the equation of the line if we wanted to actually write it out. What I have now is, in fact, 2 different independent variables, and I'm wondering, both of them have some statistical significance, some help, and what I'm wondering is, could I use both of these in concert to perhaps get an even better predictor of what my y value is going to be? And it's fairly simple to do that in Stata. So what we're going to do is to issue, again, a regression analysis, but this time I'm going to include both of my independent variables. So that's the command that I'm going to use, and I generate my little box here. And again, we start with looking for our p-value, and again, not surprisingly, it's very low, so we've got a really good statistical relationship here. And look what's happened to my R square. It's better than either one of the two variables alone. It's 0.9681 here, it's 0.793 there, and 0.913 up here. So by using both of those variables together, I in fact have produced a predictive equation that's even stronger than either one of those independent variables used alone. Now let's go back over here to the lower left part of our regression box, and we can see the slopes of we can see the coefficients for the two different components of our equation. So if we want to write out the equation here, it would be y equals 0.247 times x1 plus 0.119 times x2, and then we would tack on our y-intercept, which in this case would be minus 0.38. So that would be the equation that you could use to generate a value of y, and it would explain almost all of the variation, 0.9681. But here's what's really interesting about a multiple regression. If we go over here, we can see that independently, both of these factors here are statistically significant because these values are far less than 0.05. And not surprisingly, we saw there wasn't quite as good a fit with x2 as with x1, so it has a little bit higher probability, but still 1 in 1,000 that it arose by chance. That's pretty slim. So we can say confidently that there's a positive relationship between x1 and y and between x2 and y. But look at the size of the coefficient. We can see that 0.25 is essentially a little more than twice as much as 0.12. So what this is telling us is that in this predictive equation that we've developed using two independent variables, we can show that the explanatory power of x1 is about twice that of x2. So this becomes a very useful tool when we are trying to analyze baseball statistics, where we're going to have multiple offensive factors that we can measure, trying to predict what the number of runs that a particular team is going to score.